start with the presentation.
Okay, we are on live now.
Okay, thanks.
Eduardo, how will questions, how will I know there's questions? Will they come through the chat or will you get them and let me know?
They appear on the YouTube channel, so they will not show up here in the Zoom, but I will be collecting them on the YouTube channel, and whenever you make a break, I can relay them to you.
Okay, and please, if there's at some point, even when it's not a break, that you think it's important to address a question, maybe several people are confused about something, please interject. There's no problem at all. I'm happy to pause and deal with questions.
Fantastic. Okay.
Excuse me for that.
Okay, I think we're gonna start. If you don't mind, I'm gonna make the presentation in Spanish and then we'll switch back to English. Buenas tardes, bienvenidos a todos. Les agradezco mucho su asistencia. El día de hoy tenemos el gusto de tener a Ronald Walsworth, que es profesor del Departamento de Física en el Departamento de Ingeniería de Computación y Electrónica de la Universidad de Maryland. We have the pleasure today of having Ronald Walsworth, who is a professor in the Department of Physics and in the Department of Electrical and Computer Engineering at the University of Maryland. Él es también fundador del director del Centro de Tecnologías Cuánticas, que se enfoca en el desarrollo y las aplicaciones de ciencias cuánticas, que es un centro muy ambicioso que se fundó recientemente, así como de la parte de educación de la fuerza de trabajo en tecnologías cuánticas. Walsworth recibió su grado de licenciatura en física en la Universidad de Duke, su doctorado en Harvard. De 1991 a 2020 tuvo una posición en la institución del Smithsonian. De 2003 al 2019 también es parte del faculty en la Universidad de Harvard. Actualmente él es fellow de la Sociedad Americana de Física y funge como dentro del programa de viajeros distinguidos para darle charlas de la división de ciencia de láseres de la Sociedad Americana de Física y recibió el premio de Pipkin, el Pipkin Award de la Sociedad Americana de Física en 2005. Es realmente un investigador muy importante a nivel mundial y es realmente un placer para nosotros, todo un gusto tenerlo con nosotros para el coloquio de hoy. It is really a great pleasure for us to have you here. I really thank you for accepting our invitation. It's a pleasure to have somebody of your size in our colloquium. So without further postponing, I thank you again for your talk. And he's going to talk today about Oh, sorry, I missed the title of the talk.
Quantum diamond sensors. Quantum
Quantum
diamond.
diamond sensors. Thank you very much.
Okay, thank you, Eduardo. It's great to be here. I look forward to this interaction. I'll be speaking English. My Spanish is not very good. I apologize for that. And I'm going to be sharing my slides now. Let's make sure I get the right ones. Can you see everything okay?
Yes, we can see.
Okay, great. So I'm going to be telling you today about quantum diamond sensors, and I'll be making some points as to how these sensors provide the best of both worlds. I'll tell you what that means as we go along. I'm at the University of Maryland, and I lead this Quantum Technology Center that Eduardo told you about. Here's our slide that we like to show. The theme and the motto of the Quantum Technology Center is to innovate, translate, and educate in quantum technology. Quantum technology is a new field emerging in the physical sciences with diverse applications: quantum computing, quantum sensing, quantum materials, etc. The Quantum Technology Center is an application-focused center at the University of Maryland, where we're attempting to advance the technology, that's innovate. We're translating the technology to other disciplines in the life sciences and elsewhere, also into commercial entities and to governmental entities. And we're figuring out the way to educate people in the development of quantum technology, a kind of engineering and applied physics discipline using the principles of quantum mechanics, but now for hopefully high impact real world applications. It's still an emerging field across the world. It's not clear how great the impact will be of quantum technology, but it's clearly very interesting, and many of you probably find it interesting too. Recently, the University of Maryland has built a significant new building, the Fernandez Idea Factory, which is the new home of the Quantum Technology Center. I show these nice photographs here, both during the day and during the evening. Last week, the building was dedicated, and we're in the process of moving into the large laboratories there for the Quantum Technology Center. We also are hiring a series of new faculty in multiple departments to be, many of whom will be part of the Quantum Technology Center, both in the basic sciences and in engineering departments. Okay, so my talk today is about quantum defects in diamond, and there are many applications. This beautiful image that you see here is of small diamond grit. Each of the particles you see is about 10 microns in size, and this is a pile of grit. It's the sort of diamond grit that's used in industrial processing, in grinding, etc. Because diamond is very, very hard. It's like sand, but it's very hard sand that is used for grinding. And in this case, the diamond grit has just been illuminated with ultraviolet light, and a color camera is taking this lovely photo. Inside of the different diamond particles are defects, disruptions in the lattice structure of the diamond, and sometimes substitutional atoms or vacancies inside the diamond lattice. And the different defects lead to the different colors that you're seeing, because they, based upon the laws of quantum mechanics, can absorb and emit light at different wavelengths. They tend to absorb the UV light quite well, and then these different defects emit different colors of light. In particular, the defect known as the nitrogen vacancy color center, the defect I'm going to focus on in this talk, tends to give off red light. So when you see a lot of reddish light being coming out of these particles, that's these NV centers, many of them inside of them. And I'm going to tell you about NV centers in diamond and how they can be used for quantum sensing. The NV in particular has special properties. I've mentioned that it can absorb and emit light, and really it provides an optically probed sensor of things like magnetic fields, electric fields, temperature, pressure that the diamond is exposed to, strain inside the diamond lattice, and forces, a wide range of different things that it can sense very precisely and with high spatial resolution. Now I'm going to focus on the NV center, but to emphasize there are many, many other defects that exist in diamond and in other high bandgap semiconductors like silicon carbide, which have somewhat similar properties, somewhat similar quantum properties. The NV center is the most well understood and the most widely used for quantum sensing. And it's a particularly nice one for these applications but there's lots of promise in the other defects inside of these materials. So much of what I'm going to tell you today can also be applied to some degree to these other defects. NV centers in diamond have, over the last 15 years or so, developed into what I call a platform quantum sensor, a widely used modality in many areas of basic and applied sciences. I show you here some highlights that my research group and my collaborators have been involved with across different areas of the basic sciences, from WIMP, dark matter and neutrino particle detection, and condensed matter physics, to things in the life sciences, clinical bioassays, being able to measure the action potential and the associated magnetic field coming from a single neuron outside a simple living animal, and all sorts of other applications, some of them quite practical and real world, like doing failure analysis and being able to image inside of semiconductor chips as they're operating and seeing the patterns of activity within inside them. There's a wide range of applications, and the ones I'm showing you here are in fact just a small subset. These are just the ones that I've been involved with and my research group has. There are dozens of groups around the world, perhaps hundreds, using this technology in all sorts of ways. And the technology has matured enough that in some of those applications, tools, the technology is being commercialized for various kinds of applications. I show some of them here and note the areas where there's some commercialization. I'll mention that as I go along. Now, the fact that it's mature doesn't mean it's the end of the scientific road in a way. There's a lot of work still to be done to develop this technology and make it realize its promise. So I'll try to emphasize that as I go along too. But this is one of the more mature quantum technologies that are out there, these NV centers in diamond. And really, this is why I subtitled my talk, Best of Both Worlds, really kind of version 1 of what I mean by that. There'll be a version 2 later. It's that this platform quantum technology has diverse applications in basic science and the real world. So in the basic science world and out there in terms of the practical applications in the so-called real world, these quantum technologies can be useful. Let's back up a little bit, and I want to give you a little bit of history and talk about the people who did a lot of the first demonstrations that these NV centers in diamond were useful for sensing. Nearly 15 years ago, in laboratories and about 15 years ago in laboratories at Harvard, postdocs and graduate students working in 3 groups, my group, as well as my colleagues Misha Lukin and Amir Yacobi, all faculty at Harvard, in 2007 and 2008, did some pioneering experiments that showed that NV centers were useful for sensing magnetic fields outside of diamond. That was demonstrated in this paper published in Nature in 2008, and also outlined what they might be useful for in the future as you scaled up and improved their properties. And that was outlined in a second paper in Nature Physics in 2008. This photograph of the young people, the postdocs and students who worked on some of this kind of activity and were extending it at this time, was taken in late 2008, gathered in one of the laboratories where some of the work happened. One of the key people wasn't there that day. I insert his photograph here in the corner. At the end of my talk, I will tell you what happened to these people, where are they now, and I hope you will find that very interesting. But I do want to emphasize that though professors lead research groups and sometimes have the key ideas and help train the students, it's really the younger people, the students and the postdocs, who are doing a lot of the key work, and that was certainly true here. Let me also note that at the same time that this work was going on, pioneering work at Harvard, there was very similar work happening independently by a group in Stuttgart in Germany, and also folks at IBM Research Labs in California. The community of people working in quantum diamond sensors has grown from these first few groups in the early days, but it's a very healthy community with a lot of good collaboration and people being quite respectful and helping each other as they can. This is a chunk of diamond, a few millimeters in size, filled with these NV centers and being hit by a laser pointer. You can see the green laser pointer light, and you can see that the diamond is glowing pinky red. That's what NV centers do. They absorb green light and they emit red light. And I'm going to tell you a little bit why and how that's useful now for sensing of things like magnetic fields, temperature, etc. First, a little cartoon of the NV center structure. This shows you a stick and ball diagram of the carbon lattice that's typically inside of diamond, with each of the little balls indicating a carbon atom. A perfect lattice would just have everything being carbon in all the appropriate places in the lattice. But an NV center, a nitrogen vacancy color center, is two neighboring carbon atoms which have been replaced by a nitrogen atom and a missing atom or a vacancy. This leads to special quantum mechanical properties localized around the NV center in the electrons that come from the nitrogen atom and also the neighboring carbon atoms. It's really a many-body effect in this lattice that acts kind of like an atom. It is like an atom with quantum properties similar to an atom, but now, if you will, frozen or held inside of this solid state lattice. NVs were known, as well as other color centers and defects, for decades and were characterized in terms of how they affected crystal color and quality for gemstones. But it was only in the last couple decades that their quantum mechanical properties have been understood and then begin to be exploited in things like sensing. In particular, the NV center is energetically favored. That is, if there are nitrogen atoms, remember, nitrogen is next to the carbon atom on the periodic table, and so nitrogen is a common impurity in diamond. If there's a nitrogen atom inside of a diamond replacing a carbon atom and a missing carbon atom or a vacancy, and you heat the diamond up to about 1,000 degrees Celsius, the vacancies will mobilize, and it's energetically favored when they come next to a nitrogen to stabilize into an NV center. You can then cool the diamond back down, and you can have one or many of these NV centers, depending upon how you grow or fabricate the diamond. It's also energetically favored for the NV center to pick up an extra electron from the lattice, which is why I indicate it as an NV minus. So the NV center, which is useful for sensing that I'll be describing in this talk, is always the NV minus. That's the energetically favored state. There's also an NV zero, which doesn't have as good properties for sensing, but I'll be ignoring that throughout most of the talk, just talking about the NV as if it was the NV minus. The NV minus, you can think of it as having 2 electrons, so it has electronic spin s = 1. Depending upon which isotope of nitrogen is used, either nitrogen 14 or 15, you will have a nuclear spin of I = 1 with quantum number 1 or 1/2. This will lead to hyperfine structure. Similarly, inside the diamond lattice, NVs can, given the structure of the diamond lattice, NVs can exist upon any of 4 orientations determined by the crystalline structure. This is very useful when it comes to doing vector sensing if you have many NVs, because the different projections of, let's say, a magnetic field along the different crystalline axes and the NV axes will give different energy level shifts and different properties you can use for vector sensing, as I will explain. So let me, as I here, pause and also say, I'm sorry, and I apologize to the life scientists in the audience. This is the physics-heavy part of the talk where we try to describe the basic underlying physics of the NV center. We'll get more into the applications and some of the life science applications as we move along. So as I mentioned before, the NV is a many-body phenomenon, but you can think of it as if it is like an atom held in an inert solid, in that it has properties such as that it's quantized energy levels, it's a single photon emitter, it has electronic spin and nuclear spin. The properties I'm going to describe to you are very similar over a wide range of conditions. It can operate under, the NV has its properties under ambient room temperature conditions, but also extreme conditions, very high temperature, very low temperature, very high pressures in presence of radiation and other changes. This also expands the utility of the NV center in diamond as a sensor. As I mentioned before, NVs tend to absorb green light and emit red light. And the red light emission and the rate of fluorescence that the NVs are giving off in the presence of green light illumination, that's the measurable. That is the thing that the experiments are always measuring or imaging. So the intensity of the red light per NV gives you information about its environment, like the local magnetic electric fields, the temperature that's exposed to, et cetera. And because the NV is literally atomic scale, an individual NV will give you information about these things right around in its neighboring location at this angstrom scale. So you really can get nanoscale spatial resolution in certain conditions. Sometimes people use NVs in tiny nanodiamonds, like shown in this electron microscope image, where you might have one or a few NVs inside of nanodiamonds. Perhaps you would take those nanodiamonds and put them inside of a living cell or a living organism, as has been done in some experiments to map temperature inside of organisms such as C. elegans in the presence of different biological processes and different heating processes as local thermometers inside of different parts of an animal. Sometimes you might grow a small nanodiamond pillar, as shown here, that maybe is 100 or 200 nanometers long, and have a single NV just a few nanometers away from the end of the tip, and then attach this nano pillar to an object which is controlled by piezos to be able to scan over the surface of some object of interest. And you can make a scanning diamond atomic force microscope and, for example, map the magnetic or electric fields coming from some sample that's right below and be able to do extreme high spatial resolution mapping of magnetic fields and electric fields coming from graphene or some multiferroic or some other material of interest, superconductors, et cetera. And there's a wide range of research using that kind of tool. Sometimes, like in this movie of the chunk of diamond or in this image here, you may use a macroscopic diamond that's filled with many NVs, an ensemble of them. The more NVs you have, the more signal you get and the better sensitivity of the sensor you have. Although you'd lose spatial resolution, you just have a bulk sensor. You can also have the NVs just grown at the surface layer of a bulk diamond and use it for wide field imaging and microscopy. And I will talk a great deal about that as we move forward. Really, however, you can now see version 2 of what I mean by best of both worlds. You can have near ideal quantum behavior of atoms, quantized energy levels, etc. But now not in free space, held in a vacuum chamber or a glass cell or something, or a laser tweezer, but inside a robust solid that can operate at room temperature and in wide-ranging conditions. A solid diamond that can be shaped into a wide range of shapes from the nanoscale to the macro scale. And so it can be the host that can carry the quantum object. Rather than a vacuum chamber, you have this solid that is very robust and can be interface with the real world and interface with a wide range of samples. Okay, now what I'm showing you is a cartoon of the energy level diagrams that make the energy level diagram of the NV center, showing the key processes that are relevant for doing sensing. And in particular, one of the main techniques that are used for spectroscopy of the NV energy levels and to determine things like magnetic fields is a process known as optically detected magnetic resonance, or ODMR. At the bottom of this diagram, you see 3 energy levels. This is given the electronic ground state. These are the spin levels, the electronic spin levels, the MS equals 0 level, and the MS equal plus and minus 1 levels. I show the plus and minus 1 levels offset from each other as if they would be Zeeman shifted by a magnetic field. But there's also a 0 field splitting. Even in the absence of a magnetic field, the 0 and plus and minus 1 levels are offset by about 3 gigahertz due to the interactions, the magnetic dipole interactions between the 2 electrons that make up the NV electronic states, the leading order electronic states. So those are the ground electronic states. There are also the nuclear spin hyperfine structure, not shown here. Above in green is the electronically excited states. There's many of these states, but they're strongly coupled to each other by phononic interactions. And they are split, the ground and excited states are split by an optical transition, so that if you illuminate the NV with any reasonable optical color from the yellow to the near blue, but for example, green, the NV will tend to absorb green light. Within a picosecond, it will rapidly decay down to the bottom of this vibronically excited band of states. And then one of two things will happen to the NV. It'll either emit a red photon and undergo fluorescence. That's a radiative decay. That process, the whole process of the decay in the picoseconds and then the nanosecond scale fluorescence tends to be spin preserving. So if you start in the m=0 plus or minus 1 levels, you'll absorb a green photon and emit a red photon and return back down to the level you started from. But the second decay process, shown with the dashed wavy orange lines, is a non-radiative spin-changing decay due to the modest spin-orbit interaction that exists in the excited band here. So it's non-radiative, non-spin preserving, and happens over several hundred nanoseconds. And it tends to be favored for the plus and minus 1 levels and tends to change their spin on the process of decay down to m=0. So to repeat, 2 decay processes. And if you're in m=0, really only 1. You absorb green and you radiate back down to 0 without changing your spin state. You emit photons, red photons. Plus or minus 1 levels have about a 50% chance to return to where they started and emit a red fluorescence photon, or non-radiatively decay down to m=0 on a much longer time scale. So the difference in the decay pathways between the 0 and the plus and minus 1 levels leads to some very important consequences that I'll mention in a second. First, though, let me note that the electronic spin Hamiltonian in the ground state is summarized by what I show here. There is the zero field splitting that exists in the absence of any applied fields. It's about 3 gigahertz. But that zero field splitting will change slightly as you increase or decrease temperature due to the expansion and contraction of the lattice. The magnetic dipole-dipole interaction between the 2 electrons in the NVs changes. And so the shift in the energy levels of the 0 versus plus and minus 1 due to temperature, it gives some sensitivity of the NV to temperature, is the reason why it can be a good temperature sensor. Analogously, electric fields or strain, the tensor and the vectorial and tensor properties of electric fields and strain can also shift the zero field splitting, but now in a way that depends upon the projection of those components along the NV axis. And lastly, magnetic fields can differentially shift the plus and minus 1 levels in the way that I show in this cartoon and that I mentioned earlier. And because we're talking about electronic spins that make up the NV, the gyromagnetic ratio of the NV is quite large. It's a Bohr-magneton gyromagnetic ratio, which means that these plus and minus 1 levels shift rapidly with magnetic fields. So small magnetic fields can end up leading to large energy level shifts, which is why the NV can be a good magnetometer. Other key points. The electronic spin lifetimes of the NV, the spin lattice relaxation time, known as T1, and the spin coherence time, known as T2, are remarkably long, even at room temperature. It can be milliseconds long. Think about that. That's an electronic spin sitting inside of a room temperature solid with all the vibronic and phononic processes that are going on inside that room temperature solid. And still, the electronic spin is so isolated from the excitations inside the diamond because of the special nature of the NV, its small spin orbit interaction, and the fact that the NV energy level structure sits midway between the vibronic, the valence and conduction bands, that you can have remarkably long coherence times. Also, key is the ability to optically prepare the spin states and read them out, which is related to the branching ratios and the differential branching ratios in the excited state in a way I'm going to describe now. So on the left, I'm showing you some data that's taken from a single NV and repeated over many runs of the experiment. And this shows the fluorescence rate, the emission rate of red photons on the y-axis, and time in nanoseconds along the x-axis. And there's 2 data traces shown. In blue is when the NV begins in the m=0 state. And you turn on the green light, turn on the green laser, and then monitor what is the rate of red fluorescence. As you'll see here, over a few tens of nanoseconds, the rate of fluorescence on average jumps up, reaches a peak, and then depending upon the stochastic nature of fluorescence, And the timescales of that, over a course of a few hundred nanoseconds, you reach a kind of steady state population between the ground and electronic states, depending upon the intensity of the green light, and you get a steady state red fluorescence. So there's this spike in red fluorescence, and then you reach a steady state for the blue, which is starting with ms equals 0. In the red, you see starting in ms equal 1. Turn on the green laser at t equals 0, there begins to be absorption of the green light. The red fluorescence is beginning. It's starting to leap up just like you got with the ms equals 0, but then it hits a peak at a lower value and dips down. What's going on there is over the course of 100 or 200 nanoseconds, there's a probability to go through the second decay pathway, the non-radiative pathway that I told you about earlier. That has about a 50% probability. So on average, what happens is that the ms equals 1 level has a lower average fluorescence rate. Eventually, however, the ms equal 1 level would be pumped into ms equals 0 because of over a few hundred nanoseconds, because of the decay process. And when that happens, what once was ms equal 1 is now ms equals 0, and you get returned to the same fluorescence rate for the two states. By the way, ms equal -1 would do the same thing as ms equal 1. This is just comparing the two. So this has two key properties. One property is that in the long run, just wait, a microsecond or half a microsecond, regardless of what spin state you began in or any mixture of spin states, when the NV is illuminated with green light, it ultimately gets pumped into and placed into ms equals 0. That's optical spin state preparation. The very first thing that happens in almost every NV experiment is you illuminate the NV or the NVs with a little green light for a microsecond or so, and that prepares them all into the ms equals 0 state. That's the beginning. That allows you to do anything beyond that. Then you know you're in ms equals 0. And if you want to, you can switch to ms equal 1 or -1 with resonant microwave pulses, or you can do any kind of experiment. You start in ms equals 0. So that's one of the key things. The second one is the difference in the average fluorescence rate between ms equals 0 and 1 or -1 during this first few hundred nanoseconds, as shown in this block diagram here. The difference in the average total amount of photons that are coming out on the blue curve and the red curve, they're significantly different. That allows you to read out what spin state you were in. If you get one level of photons, you were in the ms equals 0. A different level of photons, you'd be in ms equal 1, for example. If you were in a mixture of the states, it would be somewhere in between. So with proper calibration of these sorts of things, you can tell what spin state you were in. That allows you to have a readout of the spin state. So let me show you how this kind of would work in practice. And I'll show you first for a single NV, and then later for an ensemble of NVs, when you have many NVs. Here, this is an example of data, ODMR data, optically detected magnetic resonance data for a single NV. And in this case, we have a short T2 star, this is the dephasing time. I chose data from a short T2 star example because it washes out the hyperfine structure and makes the diagram easier to understand. So on the y-axis is the intensity of red photons that are being emitted and collected in this experiment, hundreds of thousands per second. And on the x-axis is the frequency of a microwave signal that you're applying to the NV. And it's in the presence of an external magnetic field that's about 100 Gauss. So that 100 Gauss field, like shown in the diagram on the right, will split the 0 to 1 and 0 to -1 transitions by a certain amount. And you illuminate the NV with a green laser, and you're measuring the red fluorescence. Now, if the microwave frequency is in between the transitions, far off resonance of either transition, it's not on resonance with 0 to 1, it's not on resonance with 0 to -1, it's somewhere in between, and you vary the frequency a little bit, you don't see any change in the fluorescence because you're just in ms equals 0, absorbing repeatedly green photons and emitting red photons. You're at the high fluorescence rate that you get with ms equals 0. But once you come onto resonance with either transition, 0 to -1 or 0 to +1, as shown by these sharp dips, there's a competition between the microwaves attempting to drive the NV from 0 to either +1 or -1, which would have a lower average fluorescence rate, and the green laser, which is attempting to pump it back into ms equals 0, where it would have a higher fluorescence rate because you see a sharp dip right on resonance. And that splitting between the two resonances can give you because you know the magnitude of the gyromagnetic ratio, gamma NV, it will give you the magnitude of the magnetic field that is applied to the NV. And right on, as you sit on the side of the resonances, this very rapid change of fluorescence with static magnetic field or microwaves gives you a sensor of what the magnetic field is. Let me note that if you change that external field, these two peaks would shift. If you increase the field, they would split wider. If you decrease the magnetic field, they get closer. So you're really doing a spectroscopic measurement, and these sharp peaks give you the magnetic field. If you cared not about magnetic field, let's say about temperature, there would be a zero field splitting shift. And rather than the two lines shifting relative to each other, they'd both shift either to a higher frequency or to a lower microwave frequency. And so you could be able to do measurements of both temperature and magnetic field, for example. Key things here, of course, how many photons are you getting? Shown in red, the rightmost red arrow. What is the contrast? How much is the change from the high fluorescence to the low fluorescence? You want that to be as sharp a change, as big a change as possible. And how narrow are those lines? You'd really like these T2 stars and the T2s to be much longer, so you get very narrow lines. So the more photons, the greater the contrast, and the narrower the lines, the better a sensor you have. The more change in the measurable, the red fluorescence, you have with the thing of interest, let's say the magnetic fields. Here now is a similar ODMR plot, but now for an ensemble of NVs, with many NVs with relatively long T2 stars and T2, and also the NVs along all four crystalline axes inside the diamond. And so again, you have the red fluorescence on the y-axis and the frequency of the applying microwaves on the x-axis, and there's a static magnetic field that's being applied. Depending upon the direction of the static magnetic field that's applied, you can either have the four NV axes resolved, and their different ODMR splittings resolved because there are different vector projections along these axes, as shown in these four pairs above in red. Or you can have the projection of the static field be the same along the four NV axes, and then you get even better contrast, as shown in blue here, but you don't get the vector information because you're getting equal projection along all four axes, excuse me. Let me also note that you see the three dips coming from the nitrogen having I = 1. In this case, it's a nitrogen 14 that is making up the NVs. And so that shows you the fine, hyperfine structure. In the actual measurements that we do, there's information in each of these dips and each of these sharp variations. And so we often, if we're looking for small changes in fields, we'll often be dithering across these different sharp features, and we're looking for very tiny changes in these features. So we don't typically scan across the entire spectrum. Once we know where the features are, we sit right on the edge of these and we look for small changes in the fluorescence, which can give us information about small changes in the magnetic field, either with position, if we're doing an image, or with time, or both. So what is special about NV diamond magnetometry compared to other sensors that you might use? Well, it's really this combination of high spatial resolution that's possible given the atomic scale of NVs, the good sensitivity that's possible given that it has this Bohr magneton magnetic moment and there's long coherence times. You can create NVs over a bulk diamond and have a wide field of view, and it's a pretty simple device, a pretty simple technology, I should say, which is a good thing. It means it's more practical. This simple chart here shows one of the key parameters, the spatial resolution on the x-axis, and the magnetic field sensitivity in Tesla per root Hertz on the y-axis, with better sensitivity as you go down and higher spatial resolution down to 1 nanometer as you head towards the origin. And I show approximate regimes in which different classes of sensors are useful. Hall sensors for magnetic fields, for example, squids, cryogenic squids, atomic vapor cells, and diamond, typically where it operates from a few millimeters down to sub-nanometer length scales. And there's overlap to some degree of these different technologies and reasons why their sensitivity gets worse as you go to higher spatial resolution that differ for the different technologies. But I hope you can see what's special about diamond in that it provides very good spatial resolution in many cases and reasonably good sensitivity. It also, because it can operate at ambient conditions, can do things that are difficult, for example, for squid sensors or atomic vapor cell sensors, like measure the action potential of an individual neuron inside a living animal, rather than and things like being able to do NMR at the length scale of a single cell or a single protein. I'll talk a little bit about that as we move along. Another key feature, though, because the NV exists in this diamond host and can be brought to within a few nanometers of a signal source, like, for example, the NMR signal from one proton, because the strength of signals fall off with separation with some power. The fact that you can bring the sensor into close proximity can boost the signal. If you can get close to a signal source, that signal gets large. And the background noise that might exist in your environment doesn't change. So you can really increase the signal to noise due to proximity. This means often for these sensors, despite their good sensitivity, you don't need to do magnetic shielding. You don't need special apparatus because of this close proximity. It's a key advantage. Some of these other key features I've already discussed. And of course, it's not just magnetic fields. There are all other things that can be sensed, but I focus mostly on magnetic fields in this talk. All right, I'm going to pause now before we go in to talk about different applications of this technology, some example applications. I'll pause, and Eduardo, if you'd like to ask me questions. I have tried to go through both in a little detail, not too quickly, but of course it's hard to get if you haven't seen this before. I'd be happy to answer people's questions at this point.
Okay, so feel free to post your questions as the talk goes by on the chat. Siéntanse en libertad de poner sus preguntas. So I have here a few. Let me start with the basic ones. Why diamond and not some other base, like for example, silicium or something else? What is special about diamond? Okay, so as I mentioned towards the beginning, diamond isn't unique. There are other materials in which these defects are found, but they tend to the defects that have the good quantum properties, you'll tend to have them energetically separated from both the valence and conduction bands in some semiconductor. So the NV happens to be energetically found somewhere in the middle of that. So it's a large, wide band gap semiconductors. It's a kind of a desert for electronic excitations there. That's good in the sense that the defect now is decoupled for the electronic degrees of freedom. So that's one thing. If there are lots of electronic degrees of freedom in some other material, then there are ways to lead to decoherence and alter the optical properties in ways that are probably not going to be atom-like. You won't get the defect to maintain discrete energy levels and have all these long coherence times. Then there's also, so that's electronic degrees of freedom. Then you'd say, well, what about phononic and vibrations that go on in the crystal? There, it turns out that that matters too, and that absolutely is one of the primary leading sources of degradation in the optical and spin properties. But there, the NV in particular has a very modest spin orbit interaction due to a cancellation of various effects that have to do with its structure. So it's good that it's non-zero, but it's also good that it's not too large. If it was larger, you tend to have shorter coherence times and shorter spin relaxation times. The spin would couple to the lattice more and everything would happen faster, and that would take those spectral lines and broaden them, and then you would not have as good a sensor. However, you don't want the spin orbit to be zero because you need that difference in the decay pathways to be able to optically prepare and read out the spin states. So it's sort of like a balance of just not too hot, not too cold, not too much, not too little. And the NV turns out to have a near optimal balance. And some of the research that's being done into the hundreds of other defects that exist in diamond and in silicon carbide and other wide band gap semiconductors are to find other defects whose properties might be even better than the NV. They might be different. They might have only sensitivity to some of the things and have zero sensitivity to others, like no sensitivity to strain, but yes, sensitivity to magnetic fields. So there are other silicon vacancy is another defect in diamond, germanium vacancy in diamond, tin vacancy in diamond, and some other ones that are interesting for other applications.
There are a variety of vacancy-based defects in silicon carbide that people are pursuing for similar sensing applications, and a whole research and development program in many groups. For example, David Oshalon's group at Chicago does much of this. Natalie De Leon's group in Princeton and many others are investigating the other defects in these materials. But so far, for the actual applications, or most of them, the NV is still the best. That may not always be the case, but it's at this point, due to this trade-off and balance of factors.
So in a related question from Edgar Cerda, could we briefly comment on the specific comparison of diamond versus boron nitride?
Yeah, so for boron nitride has other very useful properties, and it has interesting, a number of them have interesting optical properties too, but I would say for the sensing applications that we're talking about here, where you want long spin lifetimes, good optical contrast, etc., and diamond, or the NVs in diamond are the best. Diamond still has its challenges. It's the growth of individual diamonds with individual NV properties is not super reproducible. It's still a little bit of a boutique process. There are laboratories and companies working on making very reliable fabrication of diamond, but is nowhere near as reliably reproducible as other more advanced materials. Diamond isn't that expensive, although people think of it as expensive because of gems. The gems, you might know this, but the gemstone market is, the prices are kind of artificially kept high by a cartel so that they can extract the maximum money from working people. You might have wondered why it's just barely possible to buy a diamond ring if you work really hard. Well, that's not an accident. That's done to extract money from people. But for scientific applications, diamond is, I mean, it's not the costs of the diamonds aren't the problem. It's making them and fabricating them better. One of the things we're trying to do, myself and others in the community, is help this process so that anyone could get access to the materials, and it not just be a few special laboratories have the special diamonds to do the special work, but that everyone can get the same materials and science can advance more.
Fantastic. So on that same topic, we had the question with my students, how do you create the NV vacancies?
Right. So I hinted at this a little bit, but let me go through. There are two general classes of processes to make diamond in laboratories. We're not typically talking about diamonds dug out of the ground, of course, although some of those diamonds would have NVs in them too. That's not what we're talking about. So one class of making diamond is called high pressure, high temperature, which in a laboratory somewhat mimics what happens naturally, in which you expose the carbon material to very high pressures and temperatures, and you can make diamonds that way and at some scale. You can also include impurities during the process, like nitrogen, etc., and then anneal the diamond afterwards and make NVs that way. That is fine for making bulk diamonds with bulk NVs. It's not good for things like having the single NVs a few nanometers away from a surface if you want to scan, or single or few NVs inside a nanodiamond, or as I'm about to start talking about, having NVs right at the surface layer for imaging. In that case, what typically is done is people may use a chemical vapor deposition process in which diamond is grown in a plasma chamber and off of a seed, and slowly can be grown. And in that case, they can control the impurity content during the growth process and place the NVs where they want them during the growth process. Then there's a whole alternative method in which you don't grow the nitrogens and the vacancies in as you're doing it, but you implant. So in that case, you would take, for example, nitrogen ions in an accelerator with large electric fields and accelerate them into the diamond. Depending upon the energy of the nitrogen ions, they'll break up and they'll make nitrogens inside the lattice, and they'll go varying depths inside the lattice. Then you'd also irradiate the diamond with electrons, for example, to create vacancies, and then anneal the diamond, and the vacancies mobilize and find the ends to make the NVs. So to summarize, Most of the sensing work is done either with chemical vapor deposition grown diamonds with the nitrogens grown in and the vacancies, and then you anneal, or you do the implantation with nitrogen ions when you want very shallow NVs, just a few nanometers away.
Okay.
But the growth and the creation of the NVs, there are standard recipes, but it's still an area of research where people are ever trying to make them better and better. And there's a holy grail, if you will, if you think about possibly using NVs for quantum information processing, for quantum computing. Originally, people thought about that. Still, some people are a little bit. Not the sensing I'm talking about, but quantum information processing. There, you could imagine that you'd have these defects, NVs or other defects, in an array, like in a checkerboard array, and have them every few nanometers, boop, boop, boop. You'd have an array of them, and you could have a scalable little quantum computer with uniform couplings between them. Every 10 lattice sites or every 100 lattice sites, there'd be a defect. That would be wonderful and probably would work as a nice quantum information processing technology. But the growth of the NVs, whether through implantation or the chemical vapor deposition, is not accurate enough to be able to place them with lattice site control. You can control on average where they are, the average density, on average how deep they are, but not at the lattice site level. You can control to maybe a few nanometers where they are. And that's tens of lattice sites. And so you don't create a regular array, you create a kind of random grouping of them, and that's not good for quantum information processing. People are continuing to work on that problem too.
Fantastic. So I think we can continue.
Okay. So now on to some applications. And in particular, I'm going to be focusing on mostly on one modality that we commonly use called the quantum diamond microscope, or the QDM. And this shows you a photograph of one of the QDMs in our laboratory. You can see the computer monitor to the left. So you get an example of scale. It is about the size of a basketball, right? This contains these nice looking Helmholtz coils for applying a biased magnetic field. There's an optical microscope and microwave system inside and a nice apparatus. There are some electronics that sits over in a rack, but it is not a very large nor complicated device. That's good. That means it can be applied in many ways. The key components include, shown on the left, a platform on which there is a diamond placed, a macroscopic diamond chip on a platform placed in contact typically with the sample of interest. There's going to be a microwave antenna or strip line to be able to manipulate the NV states, like drive those MS equals 0 to +1 or -1 transitions. There'll be a green laser that comes in to excite the NVs. Note how I'm showing it here. It comes in often in what's called a total internal reflection mode at an angle. So the NVs are illuminated by the green light, but typically the green light does not pass significantly into the sample. This means you have the green light is not affecting the sample. And then the NVs will fluoresce, and the fluorescence will be collected with optics onto a camera, so we can take images of the NV fluorescence in different parts of the diamond and hence learn about different parts of the sample. This shows you a photograph now looking down. There's the microscopic objective. Here's the diamond. You can see the green laser coming from the side. The surface of the diamond that has lots of NVs in it is glowing red. You can see a lot of the other components. The sample has been removed here. These diamonds usually are something like this, a few millimeters on the side, about 0.5 millimeter or so in thickness, and with the NVs only at the surface layer. There's a dense NV layer, but only at the surface. Now, how thick on the surface? It could be a few nanometers to tens of microns, depending upon what you want for your certain application. This shows you a side view. So the diamond here is essentially like the same diamond I'm showing over here. The bulk of the diamond has no NVs in it. It's just a substrate. It's just useful to have that diamond there as an object to be able to control it and place it onto the sample of interest. The NV layer, shown in red, and then some sample that maybe has magnetic signal sources. It could be wires carrying currents. It could be magnetization in some sample. It could be a biological sample. and there's a certain sensing volume you're probing over. So you might be taking a field of view image. Your field of view might be a few millimeters or a few hundred microns. And the thickness of the sample of interest will set the NV layer that you want. So your 2D image resolution is often, yes, it's going to be limited by diffraction and your optics to maybe half a micron or something like that. But sometimes it won't be as good as that because the sample might be thicker. The sample might be 2 or 3 microns with magnetic features that are 2 or 3 microns, for example. And so you will choose your NV layer to be similarly 2 or 3 microns thick in that case. Why? Because if the sample features are 2 or 3 microns, you're not going to get any better spatial resolution than that in any case, because the magnetic fields from them will blur out any higher resolution image. And if you make your NV layer thicker, you get more signal and you can get better sensitivity. So the rule of thumb is to make your NV layer thickness about the same as the sample thickness. What if your sample is only a few hundred nanometers thick? Then you might do the same sort of thing with your NV layer and be limited by the optical diffraction limit. So different diamonds with different thicknesses of NV layers are used for different applications. So we have a bunch of different diamonds and we use them for different applications, which I'm about to start outlining for you, but it's the same basic setup. One of the high impact applications and one of the most mature of this, which I had not actually expected when I was, when my colleagues and I were developing this technology, is in probing the magnetic features of ancient rocks and meteorites that geoscientists look at. So this is an example of a QDM image of the magnetic field patterns that come from a thin slice of an ancient rock. It's overlaid with an optical image of the same rock, so you get both structural information and magnetic field information. The different colors in this image give you the strength of the magnetic fields and the sign of them too along the z-axis as shown in the color scale here. The geoscientists know enough about the distribution of materials in this rock that they have known that this is an interesting rock, in this case taken, I believe, from Western Australia. And they're particularly interested in the small thing in the middle called a zircon, which is about 100 microns long, and the small, tiny micron scale iron-bearing grains, which are inside of the zircon. The zircon, there is strong evidence from the geoscientist study of the isotopic ratios in these zircons that this is a bit of the ancient Earth's crust that's more than 4 billion years old. The surrounding rock material is maybe only hundreds of millions of years old, which sounds old, but it's not old compared to the more than 4 billion years old. What the geoscientists were interested in is the strength of the magnetization in these iron-bearing grains inside the zircons, because they could be reporters, they could be time machines that tell you about what the Earth's magnetic field was long ago. Those iron-bearing grains have very high Curie points, and they have evidence that by doing these sorts of measurements, that in some cases, the pieces of zircon have never been heated above their Curie point. And so when they first formed with the iron inside of them in the local ambient Earth's magnetic field way back then, they would still, the magnetization that was set at that time would give you information about the magnetic field that they were exposed to. Back then, the zircons were incorporated in different rocks. They've been ground into small pieces. They've been reincorporated over billions of years into different types of rocks. And we are finding them, or the geoscientists find them, in certain special places like in Western Australia, where tiny bits of the Earth's ancient crust continues. They're interested then in figuring out what the Earth's magnetic field was as a function of time and even space throughout the long Earth's history. Similarly, they're very interested in what was going on in ancient asteroids and meteorites that have fallen to the Earth, and they do the same sort of thing. They look at what inside these meteorites and find small iron-bearing grains, which can give them information about what the magnetic fields were in the swirling plasma dust disk that surrounded the early sun before the planets formed. And later fall into Earth. By taking these sorts of measurements, they've been able to determine things about the formation of the planets in our early solar system, again, by ancient paleomagnetism of these old rocks and meteorites. It's amazing, actually, and very surprising to me that this sort of thing works. A key aspect that the QDM has provided to them, though, is high spatial resolution in a non-invasive way. So now I show you in the dashed red circle here, the spatial resolution that they had previously, before the QDM existed. using squid magnetometers. Now, squids, of course, are cryogenic, and so the ability of the squid to be non-invasive with rock depends upon it not being in contact with the rock, and so it has to be pulled off and it loses its spatial resolution. And as shown here, this millimeter scale spatial resolution of the squid would confound the signal from the zircon with the signal that comes from other secondary materials here, and you'd get an inaccurate result. If you really want high spatial resolution mapping of the magnetic fields to be able to tell the zircon from the secondary materials, you'd need a technology like the QDM. We've been able to do similar sorts of things now, looking at how electrons flow in graphene and being able to see that it's viscous, being able to probe magnetic nanoparticle labeled cells and biomarkers, and many other applications. Time's moving along here, so I'm going to pass this topic of geoscience. A lot has happened there. It's become a quite commonly used technology. A few years ago, we were training people how to do this at Harvard. We started an instrumentation company to make QDMs for people who might be interested in buying them. If you're interested, let me know. Of course, I have a financial conflict of interest. The same platform has been used and developed in a different company, of which I'm a co-founder, for medical diagnostics. Again, a conflict of interest, of course, because I'm a founder. Here, it's the same QDM platform, but now looking at biosamples like blood, which could contain targets of interest, such as circulating tumor cells or some biomarker. A patented technology was developed by this company in which those biomarkers or cells can be labeled with magnetic beads in a way that only when the labeling happens do they give off a distinct magnetic signature. And then you take a wide field magnetic image using the QDM. So there was academic research published in Nature Methods which underlied the technology. I'll show that here. Here there was a single single circulating tumor cell that was placed into a macroscopic blood sample, placed on top of the diamond with the labeling with these magnetic beads. On the left, I'm showing you where the cell is, and this was a fluorescence image. The cell was also labeled with fluorescent dyes, but the blood sample was thick enough that you could not see the fluorescence signal. Of course, the magnetic signal is not obscured by the blood. It passes through the blood, into the diamond, into the NV layer, and gives you a clear signal. So you can easily and quickly, within a minute or so of signal averaging, acquiring the image, get single cell detection or biomarker detection. If there are many of these biomarkers or cells over a millimeter field of view, you can easily acquire that information, snap, and do an image analysis to count how many are there. So it can be quite quantitative. Sample assays developed by this company are more sensitive and specific than alternative technologies. They're fast. They're broadly applicable to anything that can be labeled with these magnetic nanoparticles. It's a relatively simple process, so you have to wash off the sample at the end, but that's all the washing. The instrument is relatively small and low cost. A number of them have been built by the company. These are real instruments that are now being tested. They're about the size of a microwave oven and seeking FDA approval in the US next year. And an improved second generation device is being developed. The challenges are the number of assays that can be done simultaneously is not as large as they would like. You want to make sure that this is highly reproducible for non-experts so anyone can use the machine and get accurate results. You want to speed everything up and make it very automated and be able to build those machines at relatively low cost and crank them out. And that's the challenges for the company moving forward. All right. This is the recap of the sensing highlights that I began the talk with. I'm going to skip over the discussion of graphene, given limited time. We've been able to show that graphene, electrons flow in graphene as a fluid, a hydrodynamic fluid, not ballistically. We're able to do that with a combination by doing magnetic field mapping. I know there's life scientists here, so I'll now give some highlights of our work that we've done in the past, doing NMR with NVs of individuals at the scale of single cells and proteins. About 6 years ago, we had a paper published in Science in which we were able to detect for the first time the NMR signal of a single protein. This was done at room temperature. It's the first time, I believe, with any technology that a single protein NMR signal has been detected. A key aspect of this success was the ability to use quantum logic. So we used the electronic spin of the NV as the sensor, and we used the nuclear spin of the NV as a quantum memory. And we would measure with the electronic spin, map that information into the nuclear spin, entangle the electron and nuclear spin. So entanglement was key. And then we would read out the information from the electronic spin. It would not destroy the information in the nuclear spin, re-entangle the electronic and nuclear spins, and then repeat the readout. So with one measurement, we could get many readouts. So that greatly boosted our signal to noise and made this measurement practical. However, though we were demonstrating single protein NMR, it was not useful scientifically because the spectral resolution was very coarse, greater than a kilohertz, which is not useful for chemical analysis. J couplings or scalar couplings within molecules are typically a few hertz or a few tens of hertz. So you need better spectral resolution if you're going to use the technology. There were technical reasons and also challenging reasons of dealing with statistical polarization inside the nuclear spins in single proteins that still need to be solved. Therefore, we switched to doing the NMR now with NVs and ensembles of NVs at the scale of individual cells, the sort of 10 micron scale. A couple of years later, we've solved the problem of high spectral resolution, and we've gotten down to about 1 hertz spectral resolution at the scale of individual cells. Not yet cells, but samples of fluid which were at the 10 micron scale. Ultimate goals are to be able to do assessment, spectroscopy, and imaging non-invasively inside of cells, monitoring metabolomics and things like that. But at this point, we'd solved the spectral resolution problem, but we really had poor concentration sensitivity, only like 1 molar. That's not sufficient, that's not good. So we moved on to being able to probe more than one hyperpolarization technique. In 2020, we showed a 200x sensitivity boost. And by last year, we've now gotten about a 20,000-fold sensitivity boost using a technique known as Saber hyperpolarization. This now got us down to about 1 millimolar concentration sensitivity at this 10 micron scale. That's pretty good. We want to still get down into the micromolar scale and then apply it to individual cells. And so that's why for this and other applications, improved performance is still needed. If you remember this chart that I was showing earlier, this is where we want to get to, kind of 100x improved performance for ensembles, bettering the sensitivity, which would open up a lot of applications, including useful, hopefully, single cell NMR and imaging too. We published a paper a couple of years ago in Reviews of Modern Physics where we outline a path to get this 100x sensitivity. Includes optimizing the material properties, which we're well underway in doing, making the diamonds even lower strain, lower impurity density. It's a lot of material science work. But we're also been working on quantum logic techniques applied to ensembles to give another 10x sensitivity boost, and I'll highlight that as my last topic here. This is called quantum logic enhanced sensing with ensembles. We have a paper on the archive which you can read, posted a couple months ago. Here we exploit the long nuclear spin relaxation time in the N15 inside of each of the NVs of 1 billion NVs that are in this 10 micron scale volume. So each NV has a sensing qubit and a memory qubit. This shows the quantum logic that we undergo. I outlined it previously for the single NV experiment using single proteins. It's a similar idea here, but we've altered it and adjusted it to make it work for ensembles. We first measure the AC signal that would be coming from the NMR sample, or in the test case from a signal coming from an antenna that we're using as a test signal. Then we swap, once that information has been measured by the NV and it's an accumulated phase on the electronic spin of the NV. We swap that information with a swap gate onto the nuclear spin. We then apply a C0 to each of the NVs in the ensemble. We do it uniformly to all the NVs. That entangles and essentially correlates the electronic and the nuclear spins. And then we measure the entire ensemble, and we can repeat that measurement many times after re-entangling. So the information is basically read out with the electronic spin. That information is mapped back from the nuclear spin into the electronic spins, and you repeat the measurement. So for every measurement, you get measurement of the signal of interest, you get many readouts, you get many more photons. The next net result is about more than a 30x SNR enhancement. We did this in a kind of correct way where we were taking the same amount of total experiment time when compared to traditional measurements where you don't do this quantum logic enhanced technique. In green, we show a spectrum here where we applied a test signal with 3 spectral peaks Green is the detected spectrum that we get from the quantum logic technique. Blue is if you don't use quantum logic, and we've actually multiplied the measurement by 200x. You'd have to reduce the blue by 200-fold to compare it to green. So green is clearly a lot better. That means the quantum logic technique works, and we'll be applying it now to applications such as NMRs of single cells. So I'm coming to the end now of my talk. There's a lot of applications. I've been able to hit on a few of them, but there are many more. You know, each one could be its own talk. I do want to emphasize that this technology is both mature for quantum technology, so mature that commercialization is underway, while there's still much to do. There's many more applications to pursue. There's improvements in sensitivity and performance. There's absolutely defects in other materials and other defects in diamond to be explored as well. Remember this photo that I began with of the Harvard students and postdocs who are pioneering this work? So this is them back in late 2008. I want to emphasize these are the countries of origin for all these students and postdocs. They came from many places throughout the world, as you can see here. I think this is a wonderful thing. Science is an international activity, and I think it's very important that we maintain as much openness in every part of the world to people from different parts of the world. We in the United States have benefited from this greatly. Now here in 2022, many of these people are still involved in quantum science. They're next-gen quantum leaders. I show you where they are now, what they're working on. Many are faculty at MIT, Chicago, Australia, and Chile, and all sorts of places. Some are involved in government laboratories in the US, some are involved in startups. The fellow in the upper corner, Jake Taylor, was the quantum White House advisor for a number of years and is now involved in a quantum startup himself. The ones shown in reddish are still working in quantum diamond sensing. They were some of the early pioneers, and they're still pushing things forward. So thank you for your attention. I show here members of my group, current and past, who are involved in some of this work. I list some of our many collaborators. It's a wonderful community of people, the sources of financial support, and I look forward to taking more questions. Thank you.
Thank you very much. That's fantastic. That's really impressive. You guys are missing some students from Mexico.
Yeah, well, we had one fellow, one of the key people was from, and it's not the same thing, was from Chile. So, you know, there's definitely people come from Latin America who are involved, and we would love to have more. Please send your wonderful students to us.
Fantastic. So let me ask you, you mentioned several times, this is the best of both worlds. Which both worlds are you referring to? So
I had two meanings there, version 1 and version 2. One of them was the best of both worlds, and that this technology is useful in basic science and in applications. You know, some of what the geoscientists are doing, the things in condensed matter physics, but also in real world applications. The other version is that you get the best of both worlds in that you get quantum behavior of atoms, atom-like behavior, but now you're not stuck in a vacuum chamber, a glass cell, in a fragile device or a cryostat. You can have it in a small piece of a solid that can go into the real world again. So, and can be in great close proximity to your sample. It can go into biological things. So you get both quantum, but practicality. So that's kind of what I'm talking about. It's good quantum behavior, but in a very practical system, not stuck in a cryostat, not stuck in a vacuum chamber. That's the best of both worlds, but still with good quantum properties. For example, in this quantum logic sensing, we're exploiting entanglement, which is a key thing to give us a 10x SNR boost, which would, or more than 10x SNR boost. And that can't be possible without the different properties of the electronic and nuclear spins, qubits, and it can't be possible without using entanglement to basically map repeatedly the information between them in this way. So this is a truly quantum entanglement enhanced technique, but very practical and very useful. Now it's not the same thing as in quantum computing. There they have many qubits that they want to entangle in non-trivial ways. It's sort of the simplest kind of way you could imagine using entanglement, just between two qubits, although here you have a billion, it's a semi-classical ensemble of something like a billion 2-qubit sensors, but still the 2 qubits are important because they have their different properties. So the best of both worlds.
I see. Okay, thanks. So most of the sensing that you have described is the magnetic sensing part of these diamonds, and you show us that there is this labels that you can add to the biological systems. Is there other sources of magnetism directly in life sciences that one can use rather than depending on the markers?
Yes, so I'd say two other key ones are electrically active cells. Like we had shown this is a paper we had in 2016. We had a live worm, a marine worm that was whole. It was not cut open. And we were able, sitting on top of a diamond, to be able to measure the action potential, now not the effect of the action potential through the magnetic field. So you have a pulse of current, electrical current along the giant axon in the simple animal. This creates an azimuthal magnetic field that passes through the animal, is unperturbed by the animal's tissue, and can be detected with the NB. It's a little bit like a simple version, a single neuron version of what is done. It's called magnetoencephalography, where you put arrays of magnetometers around human brains and detect the magnetic fields that come from the brains. Now, that's at the coarse scale of a whole big brain, and this is being able to measure it for a single neuron inside this simple animal. So electrically active cells, neurons, cardiac cells, etc., those are sources of electrical currents that can create magnetic fields which can be sensed. If you want to measure the electric fields and the electric potential inside of such creatures, those will tend to be shielded by the ions that are inside of the biological system. So you'll typically want to put electrodes in, and then probably traditional techniques are going to be better than the NBs in terms of sensing. So it's the biomagnetic sensing will be in things like electrical currents. That's one area. We also had done, let me back up. I'm getting there. Let's see, do I have it? Yes, up here in the corner, magnetotactic bacteria. One of the first things we did in life sciences is being able to, again, using this QDM modality, look at the spatial length scale, 1 micron. And the black shows you the outline of what is an individual bacterium. We were able to look at special bacteria that create chains of magnetic particles inside. They do this naturally. And they do this to make like little compass needles that they use to navigate in the Earth's magnetic field. So magnetotactic bacteria are quite common. There are many, many species of them. They evolved billions of years ago, and they're very simple creatures, but they have chains of magnetic nanoparticles. And they're interesting to biologists, I am told by that biologist, because some of the genes which control the creation of the magnetic nanoparticles are also found in more highly evolved creatures like us. Not probably to make chains of magnetic nanoparticles, but probably related to the regulation of iron and things like this. So the biologists are interested in controlled genetic changes and how do they manifest themselves in the physiology and behavior of these magnetotactic bacteria. And it's very useful to be able to do magnetic images of them as they're living and dividing and that kind of thing. So that's another area. That's an area where magnetization exists in a living creature naturally. So we have magnetic labeling with magnetic nanoparticles for diagnostic reasons. We have these creatures, they exist, they're not most creatures, but there's some that create magnetization and use it in various ways. We have electrically active cells, which are in most, eukaryotes most will have electrically active cells, and there are also, of course, flow of ions and ion channels at cellular membranes that might be possible someday, but it's going to be very challenging. And then lastly is what I hit on towards the end, which is doing NMR at the scale of individual cells and proteins. So that's a different form of, if you will, magnetic signal. It's the RF magnetic signal that is emitted from the protons and other NMR species inside of individual molecules and living cells. Now, of course, NMR and MRI are widely used, but they have low sensitivity, and the kind of minimum length scale that you can typically probe is down to about 100 microns, right? Which has millions of cells in it. So if you want to go to the single cell level, or intra-cell, inside an individual living cell, or down to the individual protein level, you're going to need a better and newer sensor that can have that spatial resolution. And that's the direction that NVs have some strong promise on in the way that I was outlining quickly here. We've gotten to the point now of being able to get down to about 1 millimolar concentration sensitivity. The chemists or biologists who do NMR would say that's pretty good, but not great. You want to get down into the micromolar to be able to see all the relevant information carrying signaling molecules that might come and go under some metabolism processes inside of cells. So we're getting there, and we're hoping that the improvements with the quantum logic sensing will help us.
Fantastic. Okay, I think we are out of questions, but I would like to thank you again for this wonderful talk. It's really impressive, all the work that you guys have done and all the students, all the human resources that have been created and pushed in this direction.
Absolutely. Thank you. It was great interacting with people. And if anyone's interested in follow-up, has questions, or is interested in acquiring some of the technology or any of that sort of thing, please send me an email, and I'm easy to find, and I'll respond. And thank you, Eduardo, for the invitation.
We'll do it. Thank you for accepting the invitation.